Now our topic to discuss is what standing waves in a string having both the ends free. In our previous two lectures we have discussed two fixed end, then one end is free and other end is fixed, and now both the ends are free. So let us discuss this topic, that is standing waves in a string whose two ends are free. So we will proceed similar to our previous lectures. For this case, the two free ends of a string, we consider the following boundary condition. Actually, these are the two general boundary conditions. In our previous lecture, the boundary condition for the fixed end was y equal to 0 at x equal to 0, and for the free end, the boundary condition was del y del x equal to 0 at x equal to L. So we have already discussed the reason behind this boundary condition. Actually, what we need, the free end must be free from y directional or transverse force, and to have zero transverse force, means force along y direction, the free end must lie at one of the extremums. So at the extremum, since slope is 0, so that lead us to consider this boundary condition. So this boundary condition is just signifies that y directional force on the free end is 0. So since in this case both the ends are free, so our boundary conditions will be del y del x equal to 0 at x equal to 0, and del y del x equal to 0 at x equal to ends. Means for both the ends, the slope of the oscillating curve must be 0. That is, the two ends of the string will be at the extremum, and this will happen for all time. So we will apply this boundary condition to the general expression for standing wave. So if we firstly apply this boundary condition, that is at x equal to 0, del y del x equal to 0, what we will get, let us see. So first we will differentiate and then apply x equal to 0. So upon differentiation and then application of x equal to 0 case, we will get a to the power I omega t, that is t dependent part, this will be constant, we will be taking common, and here we will get I k a1 e to the power 0. So here we have substituted x equal to 0, and here also e to the power 0. So e to the power 0 equal to 1, so minus I, sorry, a should not be there, I'm sorry, we should not have a here. So you see, this is 1, this is 1, ik they are common, so we will get what, a1 minus a2 equal to 0. See here, or say a2 minus a1 equal to 0, and since this part cannot be 0 along with ik, so what we will get, a1 and a2 must be equal. So a2 minus a1 equal to 0 means a1 equal to a2. So here amplitudes are same in terms of both magnitude and sign. So a1 for a1 and a2, now we can replace by a. So now let us use the second boundary condition, that is at x equal to L, del y del x equal to 0, this case. So in a similar way, if we differentiate and substitute x equal to L, then we will obtain this expression, which must be equal to 0, and this will lead us to this expression, e to the power ikl minus e to the power minus ikl equal to 0. Here we have substituted a1 a and a2 to be equal to a. So this is nothing but minus 2i sin kl e to the power I theta minus e to the power minus I theta. So we will have k and l equal to n pi to satisfy this relation, that is sin kl equal to 0. And from this relation, kn equal to n pi by l, and that will subsequently lead us to have the wavelength of the standing wave generated in the string to be equal to 2 pi by kn, which is equal to 2l by n, and corresponding frequency for the nth mode of vibration is equal to nv by 2l. So in our similar to our previous cases, let us visualize the standard pattern of the standard wave by considering this expression, means we arranging this expression as L by lambda n equal to n by 2. So here lambda n equal to 2l by n, so we will use L by lambda n equal to n by 2. So for n equal to 0, L by lambda n equal to 0. So actually for n equal to 0 case, we will observe such type of pattern, and for the second case, that is for n equal to 1, L by lambda n will be half. See, L by lambda for n equal to 1, it will be L by lambda 1. So it would L by lambda 1 will be 1 by 2, means half of the wavelength. So this is the pattern, and here actually we need to satisfy the two boundary condition, that x equal to 0 and x equal to L must be lie at the extremum. So that is satisfying along with this relation. So half means, firstly you visualize this one, sorry, yeah. So this is the full wavelength, first quarter, second quarter, third quarter, and fourth quarter. So our relation, say L by lambda 1 equal to half, along with the two boundary condition, is satisfied by this part of the wavelength. Here the two endpoints are at extremum, and the entire length is fitted by half of the wavelength. So this is half of 1 by 4 plus 1 by 4, that is half of the wavelength. Similarly, for the n equal to 2 case, here L by lambda n will be 1, that is we can accommodate a complete wave, or we can fit the full wavelength, a complete wave in the entire length of the string. So along with our boundary condition, the visualization will be like this, means the pattern, standing wave pattern, will be like this. Similarly, for n by 3, the corresponding pattern will be like this. So in this way we can obtain the standing waves in a string for the both ends free. And if we now compare the three cases simultaneously, this is the compiled figure. Here this is for both ends fixed, this one for one fixed and one free end, and this is for both ends free. So we have already discussed all the patterns in our first, second, and in this lecture. So for different values of n, how we obtain different standing wave patterns generated in the string. Thank you.